Welcome to Sequences and Series for Pre-Calculus 11, and we're taking a look at arithmetic series, section 1.2 today. How does a series really differ from a sequence is quite simple. A series is simply the sum of each term in a sequence. So if we want to take a look at some examples of sequences, particularly arithmetic sequences, and we want to turn them into series, well, let's start with a simple one. First term of 2, let's say a common difference of 3, so that would be 5, 8, 11, etc. But instead of separating them by commas, we separate them by addition signs. So there we have it. There's an arithmetic series. We could also have a series which starts with a first term of, say, 10, and let's say we're subtracting 7. So the next term would be plus 3, then negative 4, then negative 11, etc. So what do we notice is that a series has the same terms, as a sequence. So they're exactly the same thing, except the terms in a series are separated by an addition sign or a subtraction sign, whereas terms in a sequence are just separated by commas. The notation we're going to use here is this Sn notation, S sub n. And really what that means is the sum of the first n terms in a series. This is going to be a finite series. And what that gives us is a partial sum. So because we're only adding up so many terms, we have a partial sum of a series. So what we can do is we can take a look at this series here, arithmetic series, 3 plus 8 plus 13, and let's consider a few things here. We have that the sum of the first one term, which really is exactly the same as term 1, is quite easy. That's 3. If we take a look at the sum of the first two terms, we know that the sum of the first two terms is term 1 plus term 2. Term 1 is actually just the same as sum 1. So you could think of it as sum 2 is sum 1 plus term 2. Sum 1 was 3, term 2 is 8, and we end up with 11. Sum 3. Term 1 plus term 2 plus term 3. This is where it gets a little bit interesting, or a little more obvious. Term 1 plus term 2 is already sum 2. So if we know what sum 2 is, and we're looking for sum 3, we can just add that specific term. If we don't know it, we can just add up all the specific terms. So that'd be 11 plus 13, which should end up with 24. So why don't you try and write down the same notation that I've just done, 3 columns worth, for sum 4. If we go term 1, term 2, term 3, and term 4 all added together, term 1 through 3 we could call sum 3, and therefore sum 4 is sum 3, which is 24, plus term 4, which if we calculate would be 18, and we'd end up with a sum of 42. So one little handy formula, I guess, is the sum of the first n terms is certainly t1 plus t2 all the way up to tn. That makes sense. But it's also the sum of the terms previous plus the term we're looking for. Those aren't really super important formulas, it's more conceptual, but there's going to be one overlying formula that we can use to find the sum of a series in general without having to add them all up by hand. This formula requires, and we can develop this formula, it's a nice little proof here. This formula requires that we write out the sum of the series. This sum n is term 1 plus, here's term 2, that's term 3, all the way up to term n minus 1 and term n. So term 1, if we notice, is term 1. Term 2 is term 1 plus d, that's basically just a definition of term 2. Term 3 is term 1 plus 2d, etc., etc., etc. For the purpose of this proof, we're going to be able to show it by writing that exact same series but backwards. So we start with the end here, which is t sub n. Then we add to that tn minus d. This would be tn minus 2d if we just follow the pattern. The next one would be tn minus 3d, etc., etc., etc. There's a bunch of ones in the middle we don't want to bother writing. And of course, term 2 and term 1. So this proof requires that we write out the whole series that we're going to add up, the first n terms. We write it again, but backwards. And kind of a bit of a clever move here, we're going to add these two series together. Column adding. So sum n plus sum n is 2 of these sum n's. Term 1 plus tn, if we column add down, is simply term 1 plus tn. t1 plus d plus tn minus d. Oh, fortunately the d's cancel and we're left with t1 plus tn. And you'll notice that the d's will always cancel. And what we always end up with is t1 plus tn. So every single term, when we column add like this, adds up to t1 plus tn. Simplifying this is fairly straightforward. If we factor out t1 plus tn, or we assume that the number of brackets is n, that's how many different terms there are. Finally, we're almost done here. Dividing by 2, we get a nice little formula of s sub n equals n over 2 t1 plus tn. That's a great formula. If you want to scroll down and write that in on the formula page there, we're going to make room for a second one here that we can edit a little bit. That's t1 plus tn over 2. We have another option. If we look at this formula, it's clear that we can figure out the sum of the first n terms by looking at the number of terms, n. We need the first term. We also need the last term. What if we don't know the last term? What if we wanted to replace, let's say, the last term t sub n with what it actually equals? Well, we know from yesterday that t sub n is t1 plus d times n minus 1. Let's make that replacement. So s sub n would be n over 2 t1 plus tn. Well, tn would be t1 plus d n minus 1. And just grouping like terms here, the t1 and t1, we get 2 of these t1s plus d n minus 1. So what we've done is we've taken a formula which depended on the first term and last term and number of terms, and have changed it so that it only depends on the first term, the common difference, and the number of terms. So a small difference in the formula, and we can write it down again in our little formula box here. That ends our notes on sequences and series arithmetic series. I'm going to move on and do some examples.